SSP, I can say there's basically no higher honor than being invited back to give a talk at the Wednesday seminar. So this is super cool for me. I am going to present new work today, in part because I don't want to bore Roger and anyone else from my committee who might have showed up with just minor progress on that project. But this is something new that I've been working on. And it's work that was inspired by a lot of the pushback that I got as a grad student when I started to think about integrating the brain into theories of conflict. And I'll say that there is a paper that goes with this. If you're at all interested in it, I'm more than happy to send it. And that paper isn't exactly motivated by a research question as much as it was motivated by this question. Which I received in many different forms, sometimes polite, sometimes not so polite, which is basically, can brain-level data provide anything useful for the study of international relations and conflict in particular? Now, it might sound like I'm setting the bar artificially low here by saying, like, literally, can you tell us anything of interest that is of use? But actually, this is how the question was put to me, and so I am taking it, and have taken it quite seriously ever since. Now, I'll sort of describe the skeptic's perspective in a few stages. The most, I'll say, maybe a direct version of that question I got, I think it was my second ISA. And I was a very keen young grad student, and a senior scholar had asked me, oh, what are you working on? I was saying, I'm like really interested in the brain and studying conflict. He's like, that stuff is junk. MRI is ridiculous. Like, what about the dead salmon? And I was like, I know the answer to this question. And what he was talking about was the fact that some neuroscientists had, in fact, scanned a dead salmon to illustrate a point to their colleagues. And the point of scanning the dead salmon had been, look, if you run a bunch of statistical tests, thousands and thousands of tests, you're going to get some false positives. Now, we all know the salmon is dead, it has no brain activity, and yet here are some false positive results. And so this was meant to be just a very vivid illustration within the neuroscience community of the importance of taking false positives seriously in their research. But because this sort of captured the imagination, the dead salmon traveled beyond neuroscience and was sort of distorted and twisted into a message, which was given to me by this senior scholar, that in fact MRI research itself is unreliable, that there's something wrong with it. See, they found life in a dead salmon. And although I tried to explain the statistical point underlying the dead salmon to the senior scholar, he was not persuaded, and I don't think he ever will be persuaded that there's something of use here. But the sort of data problem is something that I'll talk about a little bit more. Now, there are three other objections, at least, to the idea that neuroscience can teach us anything about IR and conflict, which I take more seriously. And in the paper, I use a framework to think about external validity of these types of studies that was sort of put forward by Agami and Hartman in a recent APSR paper. If you're thinking about methods and you're thinking about validity, it's a cool paper. I totally recommend it. One of the things that they talk about is this notion of the sample. Is the sample something that you can generalize from? Well, if you look at the people who volunteer for fMRI studies, and I have been that person, this is not representative of almost any group of people that you might care about, certainly not representative of the population as a whole, certainly not many elites in there, leaders in there. So for the folks that IR scholars are interested in, you might reasonably be concerned that the group of people that winds up in fMRI research is just not the right group of people whose brains we need to study. So that's a fair point. If you've ever participated in MRI research, has anybody done like an fMRI scan for fun? Okay, okay. They happen across campus. They can be quite fun. But if you've done them, you'll know that the actual experiment itself, the experimental paradigms, those are kind of weird too. So are the treatments and outcomes that we're observing from these studies really something that we can use, that we can make inferences from? This happens to be a screenshot of a paradigm of somebody walking through a fear-based study, and that is a picture of a giant tarantula. And so like, can tarantulas tell us something about IR, or can people's responses to tarantulas tell us something about IR? I think you can have that debate. But let's just say that you buy the quality of the data, you're okay with the sample, and you're okay with the paradigm. For those who have had, say, medical MRIs, you'll know that the setting in which the data itself is collected is also super weird, like the context in which the data is gathered. This is a selfie of me at one of our scanners here. I'm in scrubs because we do MRI experiments here in scrubs. It's a very medical, sort of clinical looking setting. And someone is going to lie down in the bore of that giant magnet and look at pictures of tarantulas. And you might think like, this doesn't seem like research that maybe is necessarily going to tell us much about the brain. But I'm going to present the cautious optimist's view that I have come to over time about why I think there is something that we can learn as scholars of IR and conflict, but actually even a little bit more broadly. And the first concerns where neuroscience is now with respect to its data and how much of it there is and how easy it is to access. So although any one study may have false positives, neuroscientists know this, and they know that better inferences can be made by pooling data. It's actually a field that shares a lot. And throughout this talk, you're going to see little footnotes on the slide that reference NeuroVault, which is a place where people go to contribute their neuroimaging data so that other people can use it in their work, thus expanding the pools of subjects that they study and the sort of robustness and sample sizes of their analysis. There are tools that allow you, without any sort of special techniques or any money, I should also add, to analyze the collection of neuroscientific studies on a subject, and not just any one. And so the way in which this is, I reference it in the paper, I call it large-scale neuroimaging data, but that's also what other folks call it. The way in which large-scale neuroimaging data is now become available and accessible, I think gives reason to be optimistic about fixing some of the problems that come from looking at a little tiny snapshot sample. The other reason I'm optimistic is I've read Perception and Misperception in International Politics, and more importantly, I have looked at the footnotes. And if you look at what the robustness of the cognitive psychology literature and the social psychology literature and the personality psychology literature at the stage that it was when Bob Jervis was using it as a very generative source of material for thinking about how to improve studies or our theories of IR and conflict. If you know a lot about experiments, you're going to be a little bit horrified. I'll just say this book was published in 1976, so you can just sort of imagine. But these are most definitely students. A lot of these studies are observational, not even experimental, which is not a knock on the book at all. It's just to say that I am more confident about the robustness of neuroscience today than I am at where cognitive psych was when it started being a tool that political scientists, and in particular scholars of IR, believed they could use. So I think we're there with neuroscience. Here's another reason that I'm optimistic, and does anyone other than Ken know who this is? Okay, so this is Nancy Kanwisher. She's a neuroscientist here at MIT. What I'm not even sure if Ken knows is that she was Bob's postdoc. So she did her postdoc with Robert Jervis, then decided to be fully blown a neuroscientist. But one of the things that I learned from Nancy when she first came to Ken's IR research methods class, when I was a first year, is that while there's not consensus within neuroscience about everything, there are certain things that you can reliably observe in a brain that you pluck off the street, more or less. And these things are often referred to as being species typical. There are aspects of the brain and how it works that are the same for all of us in here. And if you want an easy example, think about learning in your native language, how languages are represented in the brain and what bits and pieces of the brain are used for that. And I'm going to argue that threat perception is another one of those things. And in fact, because the systems for threat perception are evolutionarily conserved, they're in some ways even more species typical than language production. So there are certain things for which the person that you pluck into an fMRI study can give you information when you learn about how their brain works. That can tell you how someone else's brain works that you're not observing. That's not everything. That's not every concept, but it is some things. My final reason for optimism comes from a co-author of mine, whose name is Emily Falk. She runs a lab at the Annenberg School of Communications at UPenn. And her whole career is based on translating findings from the scanner into population-level predictions and outcomes. And what Emily's work has shown is that it is not the case that just because someone does something in a scanner or observes a stimulus in a scanner, that their behavioral response or their brain's response to those stimuli bear no relationship to what they're going to do in the real world. In fact, she's shown that how their brains respond in this weird clinical scanner setting can be a very good predictor of how they're going to behave in the world. So that also gives me cause for optimism. So for the rest of the talk, I'm going to kind of make a macro argument. And the first is this. The first part is this. Most theories of IR and conflict, I'm going to argue, already rely on assumptions about how the brain works. And I'm going to provide some concrete illustrations for that, but I'm just going to stick that blanket statement out there. We're already making assumptions about how the brain works. This new type of brain level data, sort of large-scale neuroimaging data, makes some of those assumptions testable. And testing, just as it would with any other kind of idea or theory, testing allows you to falsify or validate assumptions. And the process of doing that is, I think, productive and good if you want to accumulate knowledge. But this new brain level data can also help generate new theoretical insights by identifying things we might be missing in our theories of how these processes that we're already making assumptions about, how they actually work. Okay, so I'm going to dive into the case of threat perception in part because I've argued that this is a very good case. In some ways, it's an easy case for this argument. But since I told you the bar was super low anyway for proving that brain level data can make any impact, I'm not going to pick a hard case. So I think the case of threat perception is a good one to show whether or not you can use this new brain level data to test some of these underlying assumptions. I'm then going to introduce what that type of data is. There's a lot more of that in the paper than there will be in the talk, but I'm going to try to provide the basics enough to get through. But for those who are interested in this kind of thing, I recommend actually just reading the longer version. And then I'm going to test two assumptions that I argue sit within some of our really prominent theories of conflict and show whether or not large-scale neuroimaging data supports, or to the extent to which it supports those assumptions. And then I'll wrap up. So I said I want to start with the case of threat perception in IR, but I bet when I said that term, a slightly different definition popped into every one of your heads. And part of the problem is that while threat perception is extremely widely invoked, that phrase, it gets used a lot. The Scopus query I did gave me like 1,000 publications since Bob started talking about it a lot in perception and misperception. It's used as an explanatory variable for a lot of different things. It's not as bad as power, but still. Alliance formation, crisis behavior, war onset. There's a whole bunch of things threat perception is supposedly explaining. And if we add when people invoke it as a mediating variable, so the difference between hawks and doves is to some extent the whether or not, or how many threats, or the intensity of threat perception in that group. Perhaps, and there are some theories that say, certain balances of power generate more threat perception than others. So threat perception seems to do a lot of work in a lot of places in a lot of ways. The problem is that the words are defined differently every single time. So if you took all of these works and asked, are any of them using this term in the same way, I would say odds are no. And that's a problem. If you want to understand a concept, the fact that everybody changes or customizes their definition leads to very little knowledge accumulation. For those of you who read Adcock and Collier and early in grad school, this is like bad conceptualization or conceptual stretching at its worst. Now, in the paper, I'd spend a bit of time arguing for just taking threat perception literally, using the sort of lay interpretation of this, not creating fancy definitions, using actually the dictionary. And one advantage of doing that is that that's kind of what everybody else does, and it aligns the study of IR in conflict with other fields. So what do I mean when I say taking it literally? Rich is going to hate this because I did this in my dissertation and he got so mad that I quoted the dictionary. But I'm totally sticking by this, that there is no reason to invent a new meaning for a term just to sound more academic. So the dictionary says that basically one definition of a threat is anything that seems likely to cause damage or be dangerous. And it turns out that a whole bunch of IR scholarship fits really nicely with that definition of threat. Like, it doesn't invalidate anybody's work. It doesn't call in anything into question. Most people are studying a version of this. And if they're not studying a version of this, they might be studying a more specific instance, which we see a lot in the literature on coercion and stuff. A threat can just be a statement. I issue a threat, a statement of conditional intent to harm, which is often thought of as a signal. Those are just the basic definitions of a threat. You don't need anything fancy. But if you take a literal approach to perception, you cannot ignore the brain, because perception is a process that occurs in your brain. Again, this is sort of just going back to the lay meaning of what it is to perceive. So, as I said, the argument that I make more extensively in the paper is we should just talk about threat perception like this. It's either the brain's interpretation of something that seems dangerous or the brain's interpretation of a signal that is intended to coerce. If you do that, it opens up a world of research, because defined this way, there's a ton of neuroscience and behavioral biology literature that can be leveraged. And I'll highlight specifically that there are about 700 fMRI studies since 2003 on this concept. The way that I know there are about 700 is that I'm currently conducting a survey to count all of them. Now, some folks are doing this anyway, like Rose McDermott, others who are sort of more explicitly engaged with the literature from other fields. But I would argue that we're all making these types of assumptions. We're all talking about threat perception as something that occurs in the brain, and I'll talk about aggregates and all of that stuff. But we're not taking advantage of the fact that there's a whole bunch of work out there that also studies that same phenomenon. So I've said a few times that I think we're already doing this. Any use of threat perception as a variable, because perception happens in the brain, any use of threat perception as a variable requires that the scholar who's creating that logical chain, that theoretical chain, makes some assumption about how people think about danger. You can't have a theory that involves threat perception without having some intuition about how it works. And that intuition about how people think about danger rests on assumptions about how your brain handles danger. Now, most of us, not being neuroscientists, don't actually think through that entire process, but I'm going to argue that we probably should think a little bit more about it. And here's an illustration. So if I'm thinking about the classic case of whether or not to go to war, and I'm doing the classic sort of rational choice math of, okay, I can figure out how many lives are going to be lost, and figure out how much it's going to cost me. We have theories that say, all right, what goes on in the mind when people think about those negative outcomes, those harms, is that they add them up, that there is a cost to going to war, and that it is represented by some sort of blood and treasure summation. But that is not known. That is assumed. That is a thing that we think the brain does. It's not a thing we know the brain does. And so we have baked into that very simple logic, which, as I'll show in a little bit, is core to, for example, bargaining models of war. We have an assumption about how the mind and brain work. It's just not been interrogated yet. And for those of you who only work on states and groups and institutions, I'm telling you, you can't get out of it this way. Because if you're making assumptions about how those groups behave, and you don't want to think about individuals, you're still going to have to make an assumption either about how most individuals would behave, or you can go Waltzian and you can talk about human nature and say this is how people always behave or how every brain works. Or by virtue of context, as in this institution, this is how people think. But one way or another, you're going to have to grapple with the fact that if you think threat perception matters, then you have a model in your head about how people think. And that model, in turn, has implications for the brain. So how would we test those types of assumptions? I would argue that what you shouldn't do is go Google Scholar and find the first neuroimaging study that you can that has the most citations. This is a bad approach. But I will lay out what I think might be a better approach. Now, I'm going to assume that not everyone knows what fMRI, or functional magnetic resonance imaging, is, and that you don't really want to take too much time worrying about what it is. But if you've heard of it at all, possibly you've heard of it in conjunction with an image that looks like this, which is a sort of cool rendering of a brain with a heat map on it with a bunch of blobs. And that, this is, some people would say, like your brain on something, right? So this happens to be your brain on pain. These blobs represent the difference between two conditions, subjects feeling pain and subjects not feeling pain. And it's literally just a subtraction. And then that heat map reflects a whole bunch of t-tests. Now remember, I said that false positives are important here. That's because in order to test whether your brain is doing anything special on pain, we just test whether or not there's more activation in it and how significant that activation is. That's the stats of fMRI. That's all that you need to know. But even less than that, what you really need to know is that those blobs form a pattern. And it's patterns of neural response during tasks that carry information that we can use. The patterns themselves tell us which regions of the brain are involved, and if you want to zoom in and look at a pixel of that image, which populations of neurons within those regions are involved. And say you don't want to know anything really about the brain, all you want to know is pattern A different than pattern B? That gives you a sense of whether or not the neural foundations, the bits of the brain required to do a certain thing or that are invoked by something like pain, are different. And so different patterns or different foundations can imply different exercises. So if you need different ingredients from the brain to do something, that is kind of the definition of a functional difference. And so what we can do with these types of images, even if we don't know very much about the brain, is we can compare patterns. And ultimately, a lot of fMRI data analysis boils down to pattern comparison. That's it. It doesn't have to be fancier than that. But as I said, this is one study. And the problem with any one study is that it's probably not based on very many people, so a small sample. And again, we have this concern within neuroscience about false positives. So what do? And what should, more importantly, people who want to consume data that takes the form neuroscience says that, which is often what people outside neuroscience want. Like, they want the field's perspective. They want to know, what does the field agree on? Well, this is where large-scale neuroimaging data comes in, which takes not one study, but many studies, and takes a certain kind of output from those studies, basically just the hottest part of that heat map that I showed you, take all the hottest parts, turn them into coordinates, run them through some software, and what you get out is a new map. And what this map represents is where all of those studies agree you should see activation. And it's called a concordance map. And you can think about it as representing, in some sense, the sort of closest thing to consensus that a field can produce about what it looks like for your brain to be on something. In this case, this is your brain on losing money. And I'll come back to this example of losing money in a second, but I want to highlight that I didn't need to run this study. I could, any of us could, take some time. This study's results and this map were made available via data sharing, which is absolutely free to use and to access. And so this kind of data doesn't require thousands and thousands and thousands of dollars, which I think is another advantage. So we'll talk more about this monetary loss example in a second. I'll also say, when I show these types of maps, these maps that result from meta-analysis, I'll always show them in this sort of three-dimensional rendered brain, because I think it's easier to understand, just see spatial patterns. Those slices that people show for individual studies I don't think are so easy to interpret. But I made this figure from a heat map like you saw on the previous page, just made it 3D so it would look a little bit easier to interpret. Okay, so that's one concordance map. So how can we treat these types of maps as data? Well, first of all, let's just be clear. There's no fix for garbage in, garbage out. If the studies that go into the process of meta-analysis are no good, then what you get out the other end is no good. But this puts the burden on somebody doing research to perform a little quality control through study selection and through the thresholds of inference that you set for yourself, the exact same way you would do if you were running a regression or setting the standards of inference for any type of statistical test you want to run on your data. If you decide to do your own CBMA or you want to look at somebody else's, you decide what standard of inference matters for you and you compare it to the one that's used in the test. The method itself, I think, deals with some of these concerns about validity. The sample sizes are obviously pooled over many, many studies. There are controls for non-independence, but you're leveraging data from many more people, and those people are much more diverse. So it is the case that you can study something like monetary loss, but you can study people who played those games and did those paradigms in English-speaking countries, often in China, in Europe. So you get a cross-section of essentially brains that you don't really see in other types of social science research as much. And you can vary the task or outcome if you want. So you don't, like, if you're going to do one of these things on your own, it doesn't have to be all snakes and spiders if you want to study fear. You can study all sorts of versions of that. But in and of itself, the CBMA will represent the findings, or null results, by the way, that's totally possible with the CBMA, that you can get from pooling lots and lots of data. And then how do you analyze it? Well, as I said, this is all about patterns. And so you can use methods for pattern similarity analysis that allow for statistical tests and comparisons. So it's relatively straightforward. And as I've also said, very cheap, which given what it takes to run an fMRI study here, which I did as a postdoc and had to raise half the money for, I'm going to tell you this is a huge bonus. There are also a lot of existing CBMAs. So in a recent survey, one sort of particular technique was found to have 603 published over a decade. I would say that that number is, there's at least 100 more now. This is a really common type of academic publication in neuroscience. So it's not, it's something that's sort of popular, like you can find these. And there are many free maps. So these are the data sets that I use in the paper that I reference. To test one assumption, I used, the first one I used 3 CBMAs, so it's not very many. The second required a lot more. And as you'll see, the publications themselves, like comparing these types of maps, thinking about X like thinking about Y. This is something that neuroscientists are interested in and do. And so this data is sort of readily available, more or less. And for the paper as a whole, I use about 500 studies that cover over 11,000 unique subjects. So this is very different than saying, oh, neuroscience says X based on a sample size of 12 from one study run in like 2008. And I'm happy to talk about the different methods at any point if anybody wants, but this is the data from the paper. So what can you do with that kind of data? Well, first assumption that I wanted to sort of look at was this question about how people represent essentially blood and treasure. And I thought about it initially in terms of kind of Fearon's old rationalist explanations for war and his bargaining range. And I really wondered, is it the case that every negative repercussion of conflict that we can think of, or that we think of when planning or weighing up whether or not to go to war, is it the case that death and territorial loss and all that stuff can be summarized as a cost? And is that reasonable? Does that number really do what we need it to do? And so there are 2 assumptions that I probe here. The first is it the case that thinking about harms in general, physical harm, all these other kinds of harm, including bodily harm, is it the case that looks like or is a similar mental exercise to thinking about economic loss? And the second question is, if that's a little too stringent, does it seem like evaluating these different kinds of harms is likely to give us a cost-like single unitary value? Or is it essentially a harder problem? So what does harm look like in the brain? Well, as I mentioned, this group under the publication Tan et al., they looked at a few things, and I've already shown you monetary loss. So I'm going to show that again, but now I'm going to overlay their meta-analysis of monetary loss and their meta-analysis of physical pain. So what is the average brain on pain, or the concordance, consensus about the brain on pain look like versus losing money? Yellow is monetary loss, the green is physical pain, and all you need to interpret this is not a deep knowledge of the brain, you need your intuition. And you can see that the green and the yellow do not overlap a whole bunch, and there's a lot more green than yellow. And part of that is because the representation of pain in your brain is a more complicated feat than the representation of monetary loss. It takes more parts. It is a more complex endeavor. Now, it could be that I'm just being sort of a bit too literal about this blood and treasure business. Like, thinking about pain may not be quite right. In fact, leaders may not be thinking about their own pain at all. They may be thinking about other kinds of negative outcomes. And so the other thing that I did was I compared Tan et al.'s monetary loss studies to a set of studies that looked at what are basically considered bad outcomes. So thinking about all sorts of things that are bad outcomes to you. In neuroscience, this is sometimes called having negative subjective value. So no particular problem. And this study from Bartra et al., they explicitly exclude pain. So this doesn't double dip or overlap. And what you can see in blue, which is the negative subjective value, is that it is also not particularly the same as monetary loss, and also relatively complex. In fact, it's more complex than pain. And I'll show those in sort of actual numbers in a second. But in either case, harm looks more complicated than simple monetary loss. So if we wanted to formalize that similarity, that test, we can do it in a few different ways. One of the things I did in the paper was just to look across a whole bunch of areas of the brain that are active in at least one of those tasks and ask, are the patterns of activation correlated? The answer is they are not correlated. And then also to simply just count how many functional areas are active when in that pain map and how many are active in the monetary loss map. And there are twice as many active in the pain map. And I'm not going to show the same thing for negative subjective value, but I'll give you the finding, which is that if you did that whole thing for the blue, you'd get 27 different functional regions engaged instead of 9. So negative subjective value, which you can imagine, that contains all sorts of things, reputational loss, things that IR scholars think matter, but they're not as simple as monetary loss in any sort of literal sense. And behavioral evidence, which I go to more in the paper, suggests that this type of complexity, so when you represent something in your brain and it has a lot of features or it has a lot of complexity to it, can make it hard to maintain what rational choice folks sort of need, which is the transitivity of preferences. So it's hard to weigh harms because harms have many dimensions and many features to them. Who is harmed, how severe, for what duration, and that complexity makes it very hard to calculate that one number C. So for those of you who are familiar with the concept of transitivity or who are unfamiliar with it, if you have 3 choices and A is preferred to B, B is preferred to C, then a transitive preference means I prefer A to C. But there are lots of phenomena, including, you can demonstrate this with like menu selection and stuff. Like, they're very simple tests of intransitivity. But arguably harm is one of these things. That is, we have a lot of features about harmful situations that we care about. And the problem is that we don't weigh all of those consistently across choice sets. And so we cannot assume that essentially the blood component is linearly additive. Now, what does that mean? We just throw out all rationality? No, you don't have to throw out rationality, because there are rational models of decision making that don't require that linear additivity. And one of them, one of the ones that seems to be quite successful, is heuristic models of harm representation. They better predict preferences, and in fMRI studies, you can separate out heuristic decision-making from rational choice decision-making by virtue of which brain regions are essentially active, even in the domain of deciding between threatening situations. So the implications of all of this, I think, are, I'm just pulling this quote because I really liked it from one of these papers. The fact that the brain can compute values to compare apples and oranges does not mean that it routinely does so, or that valuation is the primary process underlying choice. You don't need to reduce everything down to a cost to be able to compare it, and we don't need to assume that that's how the brain works. In fact, I think when we oversimplify how threats are represented, we risk mistaking the true complexity of the problem, the fact that it is actually really hard to weigh the different features of how harm works. We risk mistaking the choices that people make for non-rationality, but actually what we're watching is just a much more complex choice process. CBMA results also point to these promising avenues for future work, i.e. something like heuristic choice models. And I'll just say that that's the work I have in progress. But I think that it's a useful way of thinking that people can still be rational. We're not saying no to that. That their choice architecture is a function of the problem they're trying to handle, and harm is a complicated problem. Losing money is not such a complicated problem. Okay, any questions at this point? I mean, I don't know if we usually stop for Q&A, but I don't want to lose it. Okay, I'll keep going. Next example, intention inference. All right, for those of you who study signaling, so threats issued as signals, maybe in combination with assurances, this is who I have in mind in this set of tests. And in that literature, it's really common to state something that's obvious but also important, and that is that people are not mind readers. People cannot actually read one another's minds, and I think we're probably all glad of that deep down. It would be bad if we could truly read one another's minds. It's fine that we can't. But this creates a problem, because it means that when someone issues a threat to you, or you think they have, and you want to know what their intentions really are, is it credible, are they serious, whatever, the question that scholars have grappled with is, well, if we can't read minds, what is it that we do? How do we assess the credibility of a threat that's made at us? And a lot of the literature assumes that we get there via some sort of indirect path. One of the most common indirect paths to invoke is that we assume we are in a strategic game. That instead of trying to figure out someone's intentions, all we need to know are their incentives. If we know the structure of the game and the payouts, we can figure out whether or not they actually intend to do us harm. And this is something that Schelling kind of lays out in the strategy of conflict. And he's a big believer in using these sort of simulation contexts. So saying, all right, we're not going to talk about nuclear deterrence in the real world. We're going to talk about an as-if game. We're going to talk about prisoner's dilemma instead. But that's not the only way of indirectly trying to infer someone's intentions. And in fact, a lot of the sort of psych and IR literature goes a different way with it and says, well, what if we leverage the things that we can find out about people? So we can't read their minds, but we can find out other stuff. We can try to infer their traits or types. Do they seem like someone who's sincere? We can try to look at their beliefs, their worldviews, what they think about the world, and then work backwards for what they might have intended. We can try to reason about their emotional states, and are they angry? Is it fake? Is it real? Are they serious? So all of those are a way of thinking about other people, a way that scholars have argued we try to solve this problem of not being able to read minds. But the question is, do we need all that? It's a lot of extra baggage. And the assumption to test is that thinking about the intentions of those who might do us harm, so people who would be issuing threats, is that similar? Does that look like any of these proxy mental exercises? And this domain of social cognition, thinking about other people, luckily, is one of the things that neuroscience has been super obsessed with. We can take advantage of that obsession. So I use a series of meta-analyses run by Schurz and colleagues that they, again, helpfully put online in addition to their paper, to compare in the paper five different types of indirect inference to the actual question. People just trying to figure out what other people are thinking. Here I'm going to present 2 brains, just for brevity. The first is this question that Schelling raises, so strategic games. So is it the case that thinking about the intentions of someone looks a little bit like trying to figure out how to play them in a strategic game? And again, you don't need to know much about the brain to know that there's a lot more green than there is teal. There is some overlap in the green and the teal. This method of doing a meta-analysis, the reason it looks bigger and blobbier is that the method is distinct, so I don't compare it to the other one. But there's some overlap here, not a lot. Okay, what about belief inference? There's a lot more overlap here. These exercises, these mental exercises, trying to figure out what someone believes and trying to figure out what they intend, look like they're relying on a lot more of the same brain areas. Right? We can, again, sort of formally lay that out, looking across regions of the brain. There were so many tests and it generated so many lines, I just kind of summarized it all in a bar chart to show the correlations between those distributions of activity across the brain. So these are the 2 things that I've showed you, factual belief inference and strategic gameplay. And what you can see is that actually all the stuff that the people doing psych and IR were sort of positing might be a good proxy exercise. They're all kind of good proxy exercises for intention inference. They're all somewhat correlated, about 0.5, using essentially the same functional architecture. But the other sort of simulation-based frameworks are not really the same thing. They don't look like our brains trying to infer intentions. But that similarity across all of those things is potentially driven by the fact that, as I said, thinking about other people is a sort of family of social tasks. It's often called mentalizing. And it may be that it's the basic architecture of social cognition. So the stuff that just helps us think about other people, no matter what aspect of those people that we want to think about, that's driving that similarity. And so one way to look at that is to consider, okay, which bits of the brain actually are just doing that general social cognition? And what are the correlations there versus everywhere else? And what you can see here is in the black bars, they're higher than the gray bars, which is just to say that these relationships between intention inference, belief inference, emotion inference, trait inference, a lot of it is driven by the basic architecture of social cognition. That is, thinking about other people. That's just a thing that your brain can do. A lot of the same parts come online when you do it, and that is reflected in this data. But there's also something missing in this data. And it's missing from the paradigms that Schurz and al. Were studying too, for the most part. What's missing is a bit of harm, or a lot of harm, right? Because remember, the initial question is, how do we understand people who issue threats? So threats involve the promise, conditional, to hurt us. And inference is about those who intend harm versus those who commit accidental harm or no harm at all, engage specifically the left amygdala, but also, depending on the meta-analysis you use, right amygdala. Now, why is that important? I've told you you shouldn't need to know too much about the brain to interpret this. The amygdala might be a little bit of an exception, but it is absent in all of those other meta-analytic maps. So you don't need to remember the meta-analytic maps. I'm just going to tell you there is no amygdala activation in any of them, even though some of them contained inferences about really negative traits. So figuring out that people were mean or bad, figuring out that their emotions were, that they were angry or negative, right? Things that we might think are related to this issue of threats problem. And it involved strategic games where we lost money. But in no case is the amygdala active. And in fact, it's not even active for most intention inference. It's inference when people are intending harm. And sort of in single studies, not in the meta-analyses on which this is based, that level of activation, how much your amygdala is active when you're thinking about someone who intends harm, correlates with a bunch of things we might care about. How wrong the action is perceived to be, how much we want to punish the person who is intending to hurt us, how much we blame them, how bad we feel in the situation, and importantly, how overblown our sense of harm is. So harm magnification refers to the fact that if two actions cause equal, identical outcomes, but we perceive one as being fundamentally worse because it is intentional, and we want to blame and punish that person more, that desire is also correlated with amygdala activation, our willingness to see out of proportion harm. And that, I think, has implications. First and foremost, though, mind reading may be impossible, but it doesn't mean that we don't try to infer people's intentions. And the sort of theoretical intermediary step where we try to figure out how people solve this problem may not be particularly necessary, but it may also be misleading because it takes away our focus from this question of intentional harm. How do we think about people who intend harm? And it turns out that at the level of the brain, that looks unique, distinctive, because there are certain regions that are operating, and in fact, operating faster than others. So in a very small study where people got electrodes stuck in their amygdala, and you could record exactly how fast they came online, it is the first part of your brain that gets going. And so there's a theory out there that the amygdala essentially acts as a gate. It allows all of the emotional response that you have to a situation to influence other cognitive processes. And so when you think about intentional harm, that gate opens up. And as Barry would say, it's enough to start the music, I think, for something like crisis escalation. Because it means when someone issues a threat to you, you see it as harm out of proportion if that gate is open. And that is enough in some way to start a sort of escalation strategy, because you already think you've been wronged, more so than an objective observer would say. It also means that the efforts to issue credible and costly threat signals, so to make your threat super credible, what you're doing is convincing someone that you really do intend to hurt them. And if you do that, you can inflame rather than deter. And so some of these coercion failures may simply be the fact that the way our brains are wired, we're not wired to be pushed really hard and back down necessarily. We may get we may have this sort of harm magnification effect that allows us to see something that is not there. So just to wrap up, theories that include threat perception already have assumptions about how the brain works in them. The advantage, I think, to the new data is that we can translate those assumptions into expected patterns for how the brain works, and we can examine whether or not we see those patterns. And that's a process that you can learn to do. What we've also learned is that simplifying assumptions about how threat perception works risk missing where some of the action is. So whether it's that the action is in how complicated harm is, or whether the action is in how unique it is to actually think about someone who wants to hurt us. Good social science theory, according to John Bender, shouldn't violate empirical regularities about human cognition. But for a long time, those have been extremely hard to establish. It's only as we've been able to pool lots and lots of data from lots of people across lots of time and lots of situations that we can even know what those empirical regularities are. But we do have a way of doing that now with neuroscience a little bit. And I think that that's where CBMAs can help us characterize some of these empirical regularities. And that offers a new way to think about IR theories and conflict theories, but also to build and develop new ones. So thank you.
All right, thanks. Yes, Polina, why don't you start off, and if people raise their hands, I'll get you up.
Yeah, thank you so much for this fascinating. Oh, I'm Polina Bidakova. I'm a postdoctoral fellow here.
Hi.
Working on something completely different. So
Okay.
I'm absolutely fascinated by this presentation. I'm just trying to understand what we know and what we assume about the work of the brain to better understand what you just presented. Okay. So we know that different stimuli activate different areas of the brain. And from that, do we know or do we assume that they produce different behaviors? Because I'm thinking different ingredients from different countries in the world can produce pretty similar dishes. So unless you really care about a particular flavor of the dish, do you care where did it come from? And how do you establish the significance of the overlap between the different areas that are activated, not in statistical terms, but in terms of the actual meaning of behavior or assumptions that they produce?
So thank you for the question. I'm just plugging this in because I can tell it's about to die, which I think kills the screen sharing. I feel bad about that. So I've confined these examples to situations where the behavioral consequences have been to some extent investigated, though not necessarily as thoroughly as I would like. I'd love it if someone had the full end-to-end meta-analytic version of, we looked at all this brain data and we collected this other behavioral response data and we can pool all of it and tell you a full and complete story. The way that I approached it in the paper was basically, I didn't write about anything that I didn't think had a significant effect on a behavior of interest. So in terms of, for example, choice architecture and thinking about harm, there are single studies, some of them reasonably well powered, about how people behave when faced with complicated tasks, sometimes in the scanner, sometimes not. So the brain component of this is to say, for example, in the case of harm, the brain's representation of harm is complex. So we should look at what happens when people try to solve problems that have this type of complexity. Now, that doesn't mean that you can't get to complexity a few different ways, like you said, different ingredients. But I was trying for sort of relatively straightforward contrasts. With the amygdala stuff, again, that's just many behavioral studies saying, wow, when we look at this activation, when we do have behavioral data, it seems like, for example, people want to punish those who intend harm more than those who commit the same harm accidentally or show contrition or whatever. And so the link all the way down to behavior is not essentially meta-analytic in structure for lack of data at this point, but I'd hope that it would be. So I don't think that the infinite ways in which the brain's activities can be combined is inherently interesting to folks who aren't studying that. But I do think that there are particular comparisons that do have behavioral consequences that are useful.
Charles Glazer.
Very interesting. My son's trained to be a neurosurgeon, so I'm very interested in brain stuff. But so I'm convinced on the data that, I mean, it seems like that was the main issue you didn't try to deal with, is the data problem. But a different issue is like, what are we going to learn that we couldn't learn otherwise? Because one thing would be, you could look at the cognitive level, you could run all these experiments of just people making decisions in these complicated situations. And see what the results are. And you look for biases and all sorts of other things, and all sorts of theories, way better than I do that. So what will we actually gain in addition, even assuming all the data problems are right? And it's not a great analogy, but in some ways, I mean, it turns out, I remember long ago when I was studying physics, I mean, it turns out that everything is quantum, but if you want to understand something at the classical level, you can just use Newtonian mechanics, and you don't need to do a little bit the same. So what's the value added and the degree of confidence you would get compared to just doing it at one higher at a much more macro level?
It's a great question. So and I have two answers to that. The first is the answer that I give to people who say, like, why study the brain and why not just study psychology? And that is that there are many, many models of how the mind works, and they're mostly wrong, right? Like, psychologists know that. It's like not a revolutionary statement. People make guesses about how the mind works, and sometimes those things are indistinguishable, to your point. Like, 3 models could be predicting the same pattern. We don't know which model's right, but do we care? Like, if they all are accurate predictors of the pattern, then fine, we can leave it at the pattern. And I think that with respect to conflict studies in particular, maybe, we are also interested in why, and sometimes it's why because we want to intervene. And so when we have 3 models of the mind that seem okay, they seem to, at that higher level, be predicting behavior, what if we want to change that behavior? We might actually need to know which of those models is right in order to affect that change. And so how I got started in some of this work was working with people who worked with groups in conflict. So very present, pertinent conflicts. And they were trying to figure out, how do we intervene to reduce the level of conflict between these two groups? And they had many different competing theories about what could be going on. And they thought that looking at what was going on in the brain would allow them to zoom in on both the sort of accurate, more accurate theories, and also potentially pinpoint mechanisms. So in some sense, maybe that's a bit of a luxury. Maybe not everyone is interested in the why. Maybe they're interested in the why for different reasons, and not every case sort of meets that same need as something like intervention and intervention design. But that is how I got started, I think, down the path of asking why. Because if you think that a decision-making process is bad and you want to change it, so whether that's national security strategy or something else, I think it helps to take the 5 competing models and figure out which one is the one that actually gives you the most leverage on the problem if you want to change something.
You could also, you could have those models in mind and then think it, once again, do the psych or cognitive level intervention and see which works. And until you have, eventually you'll have this great understanding of the brain, but until it's pretty often, probably that macro level intervention experiment is more likely to give you confidence than.
It depends a little bit on your view of those macro intervention experiments and how much confidence you get from any one. So I don't know if you guys know EGAP. So it's like they compare and do meta-analyses of these types of essentially behavioral interventions. So set the brain aside, let's do these interventions and see what works on the basis essentially of some psychological theory. And what you often find are a lot of null effects of very expensive research. So I sort of said that neuroimaging was expensive, but running a randomized trial of a psychological intervention at enough scale to have enough power to find a reliable effect in one sample is also not a cheap thing to do either. And so if you're weighing up, if I did this first, could I get my treatment arms down to 2 instead of 4? Maybe you would do this first, especially if it were free. And so it doesn't necessarily mean you should never look at real world data to see if the intervention works. But I don't think that the reliability of those, that those studies represent a silver bullet for our understanding. And my understanding is that when you do a bunch of them, even to intervene on the same phenomenon, you don't necessarily get that reliability either. So research is hard.
James.
Hi, I'm James. I'm a nuclear security postdoc. I also relied on assumptions about reperceptioning my own work. So learning about ways how to frequently test it was really fascinating. And my question is I wanted to hear more about the external validity that you mentioned, especially in terms of how specific political experiences can affect brain functions, especially, for example, conflict and exposure to violence. So just giving short example from my work is if you assume first-hand exposure to violence can shape how people become more sensitive to potential dangers around you, and if that's supported by the evidence, by the neuroscience, then I think that suggests that we need different assumptions from people who live in conflict areas to people who are not in conflict areas. So just hearing about your thoughts.
Yeah, so the study of basically traumatic exposure, whether it's accompanied by a clinical diagnosis of PTSD or not, or whether it's childhood trauma exposure, is something that I personally know a lot of people in neuroscience who study that, who are interested in that. Over the last 20 years, the trauma-exposed population all over the world has gone up quite a bit at all sorts of levels, and the U.S. military has been very interested in studying these things too. And so the findings that I presented, and actually one of the things that you do when you do this type of meta-analytic work is you decide, do I want to include or even focus on those folks with trauma exposure to see if I get different maps? And because this has been an area of study for the last couple of decades, you could do that. And I think there is at least one. meta-analysis that does that. And so you can ask the question, okay, I'm going to expose people to stimuli that are threatening. These people are previously trauma exposed and may have clinical diagnoses, and these folks don't. And I don't want to just stick with my relatively small, often like nicely paired samples, but still relatively small. I want to know what the finding is across these decades of work. It's absolutely something you can do. I haven't done it, but it is something that can be done.
Just on this, because James, you're looking, you also have generational different.
Yeah.
So does your brain change?
Oh God, yes.
Yeah. So
Gets more holes in it.
yeah, I know that. We didn't
We've
need
established
MRIs
this.
to know that.
No, it's just where they are. It's the trick.
All right, I got a lot of people on the list. Casper, you're up next.
Hi.
Do you want to stand up, Casper?
Oh, you don't have to. It's okay.
I can't hear him.
Oh, you can't hear him? Okay, stand up.
I'm actually gonna read some of my notes while I'll sit down. So I wonder how in fMRI research these threats are conveyed. Are subjects shown a vignette? Because arguably our human brain evolved to respond to immediate physical threats. The sort of reaction or emotional responses you get from having a great white shark swimming at you are probably different from reasoning about an international crisis and how to respond to a signal. So because of that difference in responses between immediate physical danger and sort of more abstract threats inherent in international crises, how well or appropriate is fMRI research to capture what goes on when people are actually faced with real threats in the real world versus reading a video?
So there's, I guess, good news and bad news about this for people who do political science experiments. The good news is that I think that some fMRI paradigms are way better at capturing that than political science paradigms. So often when we want to know the answer to your question and all we have is a survey, maybe even an online survey, there's not much we can do other than write like a really good vignette. If any of you ever decide you want to experiment a little bit more on people, you're going to have to go through some extra human subjects training. But once you go through that extra human subjects training, you can do more things to human subjects. And so the fMRI version of studying putting people through stress or fear is much more literal than read this vignette on mTurk. It's, I will make it so you feel like you cannot breathe to scare you. I will make it so that you feel like I will put you in pain. I will show you a thing you've told me you're terrified of, and I will force you to be exposed to it. So in that sense, the ability and willingness of researchers to put people closer to the emotional states that we theorize are relevant for situations like you described, there's a lot more latitude for doing that outside the social sciences, and in part it's because like you have to sign up for extra training and carry essentially extra liability for doing that kind of work. So when I decided I wanted to do that kind of work here, like I had to take extra training in being able to mess with people, and that means, I mean, some of the paradigms are quite horrifying in a way. I mean, there are people who mimic military training exercises in the scanner and do shoot, don't shoot, first person. And all of, like, we don't get to do that on prolific or, I mean, generally speaking, that's not a way that social scientists do experiments. And yet we still think that maybe we can learn something about crisis decision making from what we do. So I'd say fMRI studies can get a lot closer to the thing that we're to the mental state and emotional state we're interested in when researchers want to.
Marika, you sound like you're sorry you missed out on the Stanford prison experiment.
No, but I will say that I mean, I take the point that like if you think that there's something that you can simulate that's remotely close to being in a room in the midst of an international crisis on in a survey experiment that you're going to run, that someone's going to take as fast as they can for $2, like, I invite you to come up with that paradigm, but I don't think that they are necessarily very good or very close. But if someone is willing to be exposed to the thing that scares them most in their life and tell me what they would do to get out of that situation, I think that's more useful.
You have follow-up on this?
Yes, I have a follow-up on this sort of also transferable lesson question. So you mentioned also this earlier in your talk about the subjects that you can actually access to. Mm-hmm. Would you see there's been a difference between the subjects that are actually signed up or interview or conducted the fMRI tests and how they process fear versus, a trained diplomat, an elite making complex decisions, taking into different accounts, because it's not just harm, like physical harm to yourself, right?
Yeah, I mean, there's a part of the paper where I deal with this question of expertise. So we're not scanning elites, and there are a couple of different ways to think about how the brains of people who have a lot of experience doing something are different from the brains of people who don't have that experience. One is that the brains of people who have a lot of experience think differently, and the other is that they think faster. And the think differently version is I recruit different brain areas because of my time and expertise in making this kind of decision. Where do you see that? You do see it in surgeons. So people who are extremely experienced surgeons, their pattern of brain activity that's associated, I guess, with those tasks looks different than people who are novice surgeons. Where you don't see it is people who are, for instance, trauma exposed or who are exposed to a lot of physical harm. They respond faster, but not differently. So I think the jury is still out, basically, for a given question that you have. So say you want to know, are diplomats better at reading people's intentions, and do they do that somehow fundamentally differently, using different neural architecture? Or do they use the same neural architecture, but they're actually just much more accurate than everybody else? Maybe they put the pieces together faster. That is, on a sort of question-by-question basis, something that can be asked. But I don't have there's no single off-the-shelf answer, because for every problem, I think the answer could be different. And part of the reason that I think it could be different also is that we can control, to some extent, our response to harm, and we can control our response in social situations. We can have incentives to do so. And the brain responses of people who are doing more of that self-management in lots of contexts will look a little bit different than people who are just letting their feelings ride. And you might think that diplomats are a great example of people who are essentially exerting more self-control. But it usually doesn't negate the first process. It just means that they're better able to control their behavior afterwards.
Chicago.
Hi, I'm Chicago Wakey. We met 12 years ago. I'm so happy to see you again and your work progressing and developing. If you remember, to ask similar questions, but I used like a message from about 2 centuries ago, so I feel very archaic. I have 3 questions.
Can you get it down to 1.5?
1.5, okay, I'll try. Okay, so one, I'm interested in sort of long-term threat perception formation, not necessarily in a crisis situation, but sort of not knowing it's a threat or not, and then formulating and forming that it is a threat. So slightly different from maybe time frame. But so the one question I have, and I'm also interested in the divergence between states, why threat perception differ among states. So you mentioned about language, native language, and the threat perception being both species typical. I didn't quite understand what you meant, but does that mean that maybe a nation or individuals in that situation experience similar things and they would process threats differently? And native language have been around for thousands of years, and maybe is that the experience that's going to fit in? That's one question. So and then the second question is you talked about people wanting to punish. Does it correlate with the means at disposal to punish or not? So if you have the means to punish this wrongdoing, does it increase either the fear or the harm, anticipated harm, or does that not matter?
So I think I'll go with your middle question first, which is about divergence between states. So I use the analogy of language and learning your native language. So the architecture for learning a language is shared. Obviously, what language you learn is going to differ. So every single person in this room might have learned a different native language. If I scan your brain while you're hearing your native language, your brains will all look very similar. And I know that because that is the experiment I got my training on here. It was funded by DARPA, and they wanted to know the answer to that question. And it turns out that across language families around the world, there's remarkable similarity in the representation of one's native language and where that happens in the brain. Paper is out of Ev Fedorenko's lab. But what the content of those languages are, right, is radically different. And in fact, just because we share that neural architecture doesn't mean we share understanding. I don't understand a language I don't speak any better for the fact that the same parts of my brain and your brain are involved. And what I meant by the analogy to threat perception is we're prepared to learn to be wary of all sorts of things. Basically, the general description is like anything that can cause or that may even be associated with a threat to like evolutionary fitness or our individual level fitness. So we're prepared to learn stuff. And the regions of our brain that are associated with learning about and representing bad outcomes seems to be shared. But what things we learn to associate with bad outcomes, what we learn to be afraid of, that differs wildly, much more so than the number of languages that exist. So something that happens to you when you're a kid teaches you to be afraid of a thing that no one else is afraid of. It does not change the fact that you are afraid of it. It doesn't undo that. The architecture that supports that is going to be the same as the architecture that supports my learning to be afraid of spiders or snakes. So that's what I meant by that question.
I've got 7 people on the list and only 10 minutes, so I'm going to take 3. And maybe if you're going to lunch, you can save your question for lunch. But Sarah, let's do Sarah, Kunal, and Daniel.
Thank you so much. This was so interesting, and I learned so much. I'm not a neuroscientist, so this might be a naive question. But my research looks at, I'm a pre-doc here, the relationship between sort of counterfactual thoughts and behavior change. So the way that people think about events that almost happened but didn't, and then how that changes their future behavior. And so I guess part of what I'm interested in has to do with what you said about the amygdala. Like when people are thinking about fictitious events or things that they're reflecting upon or ruminating upon, does amygdala activation look different than it does in the face of a threat that is actually happening? Or is there any research to show us that?
Kunal?
Kunal Singh, PhD student here, also not a neuroscientist.
I don't expect
what kind of IR questions are more suitable to address using this technique? Thinking about national security, a president here might be concerned about security of a ship thousands of miles away, and that is also national security. But would it have the urgency of the same kind, as opposed to, let's say, a dictator who gets seated out of power is brutally killed? So that I would assume that your techniques are better for the latter kind of a security problem than for the former kind of security problem, or does it also have to say something about the former kind?
Daniel?
Yeah, I'm Daniel. I'm a second year student. I'm similar to Kunal. I'm interested that you seem to be drawn to neuroscience. I'm interested there's other areas of scientific literature you think local scientists aren't drawing enough, that there might be a lot we could leverage from. And then similarly, talked a little bit about the amygdala and what was missing in some of these areas was harm in CDMAs. I'm wondering though, when you said threats are conditional on promises, have you looked at CDMAs about trust? I would imagine then that like the amygdala is not also that part of the brain that we think about like trust and safety with their threat receptor. So have you considered integrating those sort of studies into your potential analysis of like coercive threat?
How much time do I have?
Yeah, you got time.
Okay.
We'll go a little few minutes late, but go ahead.
Okay,
Whatever
cool.
you'd like to take on.
I'll just, take them in order. So the strength of response when you actually experience something versus when you ruminate about it or someone gives you a fictitious situation and you're asked to imagine it. So the simple answer is most of the time you can think about the second category of stuff as being a weaker stimulus. So the direct bodily experience of a thing versus the rumination, imagination, reflection on that thing adds a little bit of a barrier. So if you were to just say, like, is the magnitude of responses high? I would say no, it's generally not. That said, there are some, for example, emotions that it's very easy to induce. And it's very easy to induce them very strongly. And I'm not going to do it because y'all just had lunch. But I have done this in the scanner and seen that it is, for example, much easier to induce disgust rather than fear. And you can do it in someone's imagination. You do not need to present them with anything gross, whatever, but you can ask them to imagine a situation and their body will take over and it will be a pretty strong response. If you ask someone, you put someone essentially in the middle of a horror movie and say, how scared are you? You're just never going to be, like, you're just not as scared as you are in real life. So it is a weaker form of treatment for sure. Okay, what kind of IR questions is this type of technique good for? So I think that IR involves, well, when we say that we're interested in IR, we're interested in national security, we're interested in a lot of different kinds of decision-making processes that people go through potentially, a lot of different contexts in which they operate, both time-constrained, with lots of different consequences. And I think this kind of work is doable when you can pinpoint a kind of mental exercise that you think people must be performing in order for them to make a decision. So, the simplest version would be something like math. Like if I present an equation to you and I ask you the answer, I know your brain has to do math to answer my question. There's no other way through. But if I ask you, here's a scenario, an elaborate sort of war game scenario, what do you do next? That's quite an open-ended process, right? And I may not be able to, like, beforehand figure out what types of cognitive processes you are going to use to solve that problem. And so unless I know essentially what mental exercise you're doing, or I have high confidence in that, I wouldn't try this approach before or make assumptions about that. In fact, I think you'd have to ask people and investigate the processes themselves. It may be that there's just so much heterogeneity that when people are presented with these super open-ended contexts, they solve a given problem in really, really different ways. But I think when you do confront people with a fairly specific thing, like, I'm going to hurt you unless you do X, that has a form. There is something about that form that IR scholars have leveraged, its similarity, its consistency, and this approach might be well suited to that. As for other sciences and the question of trust, so there are meta-analyses of trust. I don't remember what they show. I do not think they show amygdala activation. I should say that, like, just looking at someone or thinking about someone from another group, that's not going to do it either. Like, it's not about groupness. It's not about some of these sort of more basic things. It's really about intentional harm. As for the other sciences, to be honest, I've had my plate kind of full with trying to get my arms around one. But I will say that there's a close relationship between behavioral biology, so figuring out why organisms do what they do, and under what conditions and why, and neuroscience, and I think some social science. And I have not delved as deeply into the behavioral biology literature as I would like. But if you want to start someplace and you want inspiration, read E.O. Wilson's Consilience.
So, Rich, I'm going to push you off to lunch. And so I have Nathan, who's Air Force fellow, who wants you to do a thing to show that their brains are bigger than Marine brains. And then Phil.
Pretty early on.
Yeah, we established that. And then Phil, and then Sir, I don't know, but you'll have the last question. So you three want to ask your questions, and then we'll have one last round. Yeah, go ahead, Nathan.
Mine was a crawlfold and generalization question, so I'm good.
Okay, Bill.
All right, Marika, love this. I got a nuclear deterrence question for you. On the front end, and what your research says. On the front end, you have the threat of a rare or abstract event. So what does your research say about how people are informed by very rare or abstract events? And on the second stage is the retaliation is based upon a psychological response or revenge type response. What does your neuroscience say about that?
Paul, visiting from Arizona, I used to do a lot of neuroscience down the road in Cambridge. Used to put students from Palestine and Israel together in the same room. That's not happening anytime soon. But the harder question for you, the broader question, which you can respond to lightly at this time, is AI and AI assistance in this type of research, AI guidance, and also AI modeling and simulation. What are we looking at 5, 10, 15 years down the road with supercomputing and such?
Okay, I'll take the second question first and end on Phil's. So
Sax, I wanted to bring a Sax. She did work on this, Rebecca Sax.
yeah, so Rebecca Sachs was my postdoc advisor, and her work on putting Israelis and Arabs in the scanner is basically how I got started, and that's how they roped Roger in to saying that he would work on this. And our deal was, when I was a grad student, he said he'd say yes if I went to all the meetings. And I went to all the meetings, so he said yes. So then I got some funding to do neuroscience with Rebecca. There's a lot of leverage in your yes. So there's AI based. So I'm not entirely sure I understand your question about AI. Is it that computational tools and machine learning can help us better understand the brain and model scenarios that maybe we can't do otherwise? Or is it that people's perceptions of AI and what it's going to do might matter for this kind of work?
All this stuff up, lickety-split, as you know. So the question is, where can AI really help in basic brain research regarding this to start, and what do you see in the future?
I mean, so one of the things that a lot of folks do at BCS is very extensive computational modeling of using both predictive, so not ChatGPT, but predictive modeling of patterns of brain response and also patterns of behavior in order to supplement essentially the small amount of data that you can get from people and such. And there's a lot of work in that trying to understand some of the sort of fundamental structures of the brain by breaking it down into these complex feature spaces that people can't articulate. And that is something that is done with machine learning tools. The extent to which people think about AI as a potential problem or a use case that needs to be solved as far as threat perception goes, I've heard a lot about this more recently, say like the last 3 years. I don't know of any brain-related research that investigates it directly, although there is research on how people behave when engaging with computers versus humans, and there are distinct differences. Phil, nukes, rare events. So as probably everybody has done at least once, you can imagine something that's not true and still, or hasn't happened yet, and still have a vivid emotional response to that thought process, right? You think about some worst case thing happening, maybe to someone really close to you, and you feel it, like you know that you're experiencing something that hasn't happened yet, and it doesn't feel good. And so in my research, when I study how people think about nukes, which is something that I do, I often ask things like, how dangerous is this to you? Like, how worried are you? What kind of worries do you have? And you get pretty clear responses that people, when they think about a nuclear war, even as a very, very rare event, there's a lot of consensus about the kind of problem it is, and we might all die, and that it is quite severe. And so I think that although I've never seen anybody sort of study that in a scanner, I think if you there's not much difference, I think, if you asked someone in a center and you saw, oh, wow, this response is kind of consistent with other fears that people express. But where it comes to response, so like Rose McDermott has that paper in Texas National Security Review that's like, if someone were to start this even very small, a revenge mechanism and anger are going to take over, and this is going to go very badly, but that is what is in fact at the heart of deterrence. It's not some rational calculus, it's this understanding that the human desire for revenge is going to kick in, and the reason that we don't start grief with one another at that level is that somewhere in us we understand that. And I think Rose has a point there. I've never seen it like formally investigated, so I don't know much about that. But I think that the findings regarding the amygdala, which I do reference her paper in the discussion of that, suggest that we are prone to seeing harm directed against us as being considerably greater than maybe other people see that harm. And so the notion that there is such a thing as a small scale nuclear attack probably defies the logic of the perceiver, that there is no such thing from the perception of the person who is attacked, even if everybody else can stand off and say like, oh, could have been worse. See, there's proportionality here. Like I think that this suggests that those types of escalation ladder, proportionate response arguments are unlikely to hold in the world.
Well, Marika, we could talk a lot, but I think this idea about establishing sort of what is species typical brings up a lot of questions how culture and other kinds of things can interact with what is species typical and what is the more powerful force. But that would be many courses. But I'm glad, I think, as far as SSP goes, Marika's been a pioneer in expanding some of the ways we do things here, and I want to thank you for that. So thank you for being here too.
And thank you